All right, so this is going to be the first of 4 short videos on 4 optics proof that the IBSL option G requires. And this is looking at angular magnification in certain situations. And I'm going to start with the first one, which is a magnifying glass, where you're looking through the magnifying glass at a virtual image, but you're focusing at the near point. And the question is, what is the angular magnification for that situation? Okay, and so angular magnification is defined as the ratio of the incident angle as compared to your reference angle. And for reference angle, we're going to reference the looking at the object without any optics and at the near point. So this first picture here, we're looking at just a typical object at about D distance, which can sometimes taken as 25 centimeters or 24 centimeters as your near point, but you should check that with what your teacher wants as far as what you want to have given as a near point. And typically what we do, though, is we talk about such a small angle here that we actually, to find the angle, don't do an arctangent, because this is obviously an arctangent with the opposite side over the adjacent side. But if the angles are small enough, and you can check this with a calculator, say I had 0.04 here and 25, if I was actually, excuse me there, if I was actually just taking this ratio of the sides before I take the arctangent, I'm at 0.0016 unitless. And if I take the arctangent here in radians, I get essentially the same number. And so it's interesting, in radians at small angles, you can approximate the angle itself with the tangent, also with the sine if you wanted to. But in any case, instead of taking time to do this arctangent, we save a lot of time in our proofs if we assume a small enough angle to take this approximation. So we're going to call our reference angle here HO over D, where HO is the height of the original object and D is our near point distance. Okay? Now we're going to look at this object through a magnifying glass, which is a simple single convex lens, or what I would prefer to call a converging lens. And we place our object, this is our object sitting here, and we can figure out the ray diagram. We should have done this if you're at this point without looking at ray diagrams, you should go back and make sure you understand how to do ray diagrams well before coming to this proof. In any case, here's our object, and if we look at light leaving the top of the object, light that was coming as if from the focal point will turn and be converged parallel. Light going through the center of the lens continues on. Light that is parallel will converge as if it was going through the focal length. So we have these 3 principal rays, and this converging lens, if we reverse ray trace here, we see our virtual image in the back, which is going to be larger, obviously, since our object is inside the focal length. We have a negative image distance, and our image height here is positive, meaning that it is not flipped over, larger than the original object. And I think we've all been pretty clear about this. If we're focusing these new images, this new light out here that we're seeing, at the near point, then we can label this as D here. Okay, and if we label this as D and this is our HI, I think you can see that from this triangle here that our theta I, assuming small angles, and this is drawn without small angles, this is drawn with big angles just to help make clear the triangles that are involved, but this would, in reality, would be much smaller angles, so that we can still use our approximation for small angles, and so we'd have HI over D as our theta I. So pretty powerful. What we're going to go ahead and do here is say that our angular magnification is thus theta I over theta O. I get HI, which is in this picture here, over D. If thinking back to our reference triangle, we know that theta reference is simply HO over D. And so we have this nice cancellation of our near point distances. And so one thing we can say is that HI over HO is our angular magnification at small angles, which is very nice. I can also substitute hi for d here, and I'm left with d over u. Finally, let's talk a little bit about v, where v is our image distance. And since our image distance here is d, it'd be tempting to just say d equals v, but in fact, v is going to be a negative number. And so we need to put a negative in front of it so that that negative number cancels and we're left with a positive d here, which we need. So we need to put a negative in our v here. So we get our angular magnification to be negative v over u, which we could stop at if that's all we were after. We're looking at essentially, this is very similar to our typical magnification. What we call linear magnification in this situation is actually equal at small angles to the angular magnification, which is interesting. But in any case, we're after an equation that involves our near point, our focal length. And so we're trying to get to this as our ultimate goal here, d over f plus 1. So let's see how that happens. It's very algebraic. So we take our thin lens equation, 1 over f equals 1 over the object distance plus 1 over the image distance, and we rearrange that a little bit and solve for v over f. What we're going to do is multiply everything by v. Multiply this side by v, multiply this side by v. So you'll see we get a v over u plus 1. When this is multiplied by v, we have v over f. So v over f is v over u plus 1. What's nice about that is we kind of are already running towards our form here. We want to have, if you look here, we have v over u. So this is what we want, but we want it to be negative. So if we just bring it over to this side, it'll turn negative like we need it to. So we're going to take this term, bring it to the left. That means we're going to take this term, bring it to the right. So they both have a negative introduced to them. And negative v over u is our magnification. So that's nice. Now I have magnification equals negative v over u, which was this term, equals this. So I'm left with negative v over f plus 1. We recall that d is equal to negative v. So I can substitute this negative v back for d. And I'm done. I have my d over f plus 1 is my angular magnification when I'm using a thin lens at small angles to magnify an object, and I'm focusing at the near point. So this is magnifying glass at the near point, looking at the angular magnification. And we're able to derive d over f plus 1. One quick comment about how IB questions will show up here. They will occasionally ask for the derivation from scratch. It's rare, but they can ask for it. More typically, though, questions will be asked, and simply knowing the derivation well will help you to do the questions that they ask, whether it's drawing the ray diagram or doing a calculation at this step, or perhaps doing a calculation with our final answer. It helps to understand the problem and be able to do the derivation and able to do most of the questions that are going to be asked of you on an IB question. But there we go. That's the first of 4, and I'll do the others in a moment.